Alright, chemistry, this is your video lecture for chapter 9, section 2. We're moving on from mole ratios, going to talk about ideal stoichiometric calculations. Right now we're not going to really worry about that word ideal. That won't become clear until we hit section 3. Your objectives for this section want to be able to calculate the amount of moles of a reactant or product from the amount of moles of a different reactant or product. Want to be able to calculate the mass of a reactant or product from the amount of moles of a different reactant or product. We also want to be able to calculate the moles of a reactant or product from the mass of a different reactant or product, and then calculate the mass of a reactant or product from the mass of a different reactant or product. And I hope this seems familiar from the last section's quick write, the 4 types of problems that can be solved using basic stoichiometry. In this section, that is all we will be doing. We will be solving problems, each of which will fit into one of those 4 categories. Now, converting between different quantities that are both in moles is a very simple process. We only need to use the mole ratio here. So the question or prompt or whatever is given to you is going to have some amount, and that amount is going to be in moles, right? It's the given in the problem. You're going to use the mole ratio, and again we get the mole ratio from the balanced equation. We're going to put the moles of the given on the denominator so that that species will cancel out. So we can put the moles of unknown on the numerator, so that'll be the new unit once we're done calculating.
The amount of a given substance in moles times an appropriate conversion factor is equal to the amount of the unknown substance in moles. The conversion factor is the mole ratio of the unknown substance to the known substance, which can be determined by examining the balanced equation.
So when solving mass-to-mass stoichiometry problems, it's a little bit longer. We're going to end up using 3 conversion factors, 2 of which are molar mass, only 1 of which is a mole ratio. So we'll be using the mass of the given substance, the molar mass of the given substance to convert that into moles of the given substance. Once we're in moles, we can use the mole ratio, again from the balanced equation, to convert to moles of the wanted substance, and then use the molar mass of that wanted substance to calculate the mass of that substance. So here's a sample problem. In a spacecraft, the carbon dioxide exhaled by astronauts can be moved by its reaction with lithium hydroxide, LiOH, according to the following chemical equation. How many moles of lithium hydroxide are required to react with 20 moles of CO2, which is the average amount exhaled by a person each day? So let's set the problem up. Here is the equation, the balanced equation, rather, which is more important. So the amount of information that's given to me is 20 moles of CO2. The unknown, what the question is asking me for, is the amount of lithium hydroxide in moles. So this is a mole-to-mole conversion. So all I'm going to do is take the moles of CO2, which is given, set up the mole ratio of lithium hydroxide over moles of carbon dioxide, and that'll leave me with moles of lithium hydroxide. All right, I am given 20 moles of carbon dioxide, and the mole ratio of lithium hydroxide to carbon dioxide is 2 to 1, which I can see from the equation up here, 2 to 1. So I'll set up that conversion, do my simple calculation, and I will come up with 40 moles of LiOH. Moving on, taking a piece of information that is in moles and then converting it to mass. We're going to have to use 2 conversion factors this time. We're going to take that given amount, which again will be in moles in this situation, use a mole ratio from the balanced equation to convert from moles of the given substance into moles of the wanted substance. Then my second conversion factor is going to be the molar mass of the unknown substance, because I want to record that in terms of its mass. So use the periodic table, calculate the molar mass, and set that up as a conversion factor so that the moles will cancel out and my last unit will be in grams. Again, here's that flow chart. The very first situation we did in the presentation was this second green arrow right here, from moles of the substance given to moles of the substance we wanted. But here we're actually going to start from mass. If we want to go to mass to moles, use molar mass. If we go to moles to moles, use molar ratio. And then back to mass, we'll use molar mass. Again, this is the flow chart. We have 4 different situations. You start in grams or you start in moles. You want to end in moles or end in grams. So this is a very useful flow chart as you're getting used to these types of calculations. Here's another sample problem. In photosynthesis, plants use energy from the sun to produce glucose, C6H12O6, and oxygen from the reaction of carbon dioxide and water. What mass in grams of glucose is produced when 3.00 moles of water react with carbon dioxide? So what's given? 3.00 moles of carbon dioxide. What's the unknown? The mass of the glucose that is produced. I want that in grams. So I'm going to set that up. I need a balanced chemical equation first. And here that is. Next, I'm going to set up the units first. I've been given moles of H2O. I need to go from talking about moles of H2O to moles of glucose. So I'll use the mole-mole ratio of water to glucose. And then I'll have moles of glucose, but my answer needs to be in grams of glucose. So I'll use the molar mass of glucose to convert away from moles into grams, which is what the question is asking me for. So I'll plug in those numbers. The mole ratio of glucose to water is 1 to 6. The molar mass of glucose is 180.18. Crunch those numbers. Appropriate number of significant figures gives me 90.1 grams of glucose. Let's see. If we are going the other way, converting mass into moles. So we start with a mass. So here, in order to change substances we're talking about, go from substance A to substance B, we have to use a mole ratio. But in order to use a mole ratio, our units need to be moles. We're given grams, so we need to change this into moles. The way to do that is the molar mass of that given substance. So again, look to the periodic table, calculate that molar mass, convert that into moles. Once we're in moles, we can use the mole ratio from the balanced equation to convert from moles of the given to moles of the unknown.
3 pieces of information are needed to calculate the moles of an unknown based on the mass. The mass of the given substance, the molar mass of the given substance, and the mole ratio of the 2 substances. For example, how many grams of water are produced as a result of the reaction of 824 grams of ammonia in the presence of oxygen to form nitrogen oxide? First, convert the mass of ammonia to moles using the molar mass calculated from the periodic table. Next, convert the moles of ammonia into moles of water. Look at the balanced chemical equation and see that the mole ratio of nitrogen oxide to water is 4 to 6. Using the mole ratio, find the number of moles of water produced by the reaction. In this reaction, 824 grams of ammonia can produce 72.6 moles of water.
All right, here's a sample problem for converting mass to moles. The first step in the industrial manufacture of nitric acid is the catalytic oxidation of ammonia. So we'll set up that equation. Ammonia plus O2 reacts to yield nitrogen monoxide and water. This is an unbalanced equation, I hope you noticed. So the reaction is run using 824 grams of ammonia and excess oxygen, so there's as much oxygen as you need. A, how many moles of NO are formed? B, how many moles of water are formed? So let's set this up here. So what are we given? 824 grams of ammonia. What do we want? Well, for A, we want the amount of NO in moles, and for B, we want the amount of H2O in moles. So let's start by balancing that equation. This is the appropriately balanced equation right there. For A, I'm going to set up grams of NH3 because that's what I've been given, so I'm going to start there. Set up the molar mass of ammonia as a conversion factor to get into moles. Then I can use the mole ratio of nitrogen monoxide to ammonia to convert to moles of nitrogen monoxide. For B, my setup is going to again start with grams of ammonia. My second conversion factor is, again, going to be the molar mass of ammonia, because I have to be in moles to use a mole ratio as a conversion factor. But for B, instead of converting into moles of NO, I'm going to convert into moles of H2O. So let's see what these actually look like. The molar mass of ammonia ends up being 17.04 grams per mole. And then for A, the mole ratio of nitrogen monoxide to ammonia is 4:4. And for B, the mole ratio of water to ammonia is 6:4. Now, it is true that you can reduce those mole ratios. It's completely possible. And as long as you do it correctly, your answer is not going to change. You'll still be able to get the correct answer. I, however, am going to suggest that you don't simplify those. Right? Keep them as those large numbers, because simplifying things like that is just going to add another step that you can possibly mess up on. All right, now mass-to-mass calculations. This is the largest type of conversion that you're going to do, because you're going to have to go from the mass of the given substance, convert to moles of the given substance, then use the mole ratio to go from moles of the given to moles of the unknown. Then from moles of the unknown, use the molar mass of the unknown to convert to grams of the unknown. So you're actually going to use conversion factors 3 times here.
4 pieces of information are needed to solve a mass-mass problem. The mass of the given substance, the molar mass of the given substance, the mole ratio of the 2 substances, and the molar mass of the unknown substance. For example, how many grams of tin 2-fluoride can be produced by the reaction of tin and 30.00 grams of hydrogen fluoride? First, convert the mass of hydrogen fluoride to moles, using the molar mass calculated from the periodic table. Next, convert the moles of hydrogen fluoride into moles of tin 2-fluoride. Look at the balanced chemical equation to see that the mole ratio of tin 2-fluoride to hydrogen fluoride is 1:2. Using the mole ratio, find the number of moles of tin 2-fluoride produced by the reaction. Then convert the moles of tin 2-fluoride into grams using the molar mass calculated from the periodic table. 30.00 grams of hydrogen fluoride can produce 117.5 grams of tin 2-fluoride.
All right, here's another flow chart solving mass-to-mass problems. So that means you've been given mass and your answer needs to be in mass. Here are the 3 conversion factors. Use molar mass, then use mole ratio, then use molar mass. And it's that simple, as long as you follow the units. Right? Let the units inform what conversions you need to actually carry out. So let's look at a sample mass-to-mass calculation. So we have tin 2-fluoride, SnF2, is used in some toothpaste. It is made by the reaction of tin with hydrogen fluoride according to the following balanced equation. The question is, how many grams of tin 2-fluoride are produced from the reaction of 30.00 grams of hydrogen fluoride with tin? Well, let's check out what we got. We've been given 30.00 grams of hydrogen fluoride. We want to calculate the mass of tin 2-fluoride that's produced. Again, both of these are in grams. So my solution, I'm going to set up my conversion factors first, units first, I should say. Been given grams of hydrogen fluoride, use a molar mass of hydrogen fluoride to get to moles of hydrogen fluoride. Then I can use a mole-to-mole ratio to go between hydrogen fluoride and tin 2-fluoride. Once I'm in moles of tin 2-fluoride, I can use the molar mass of tin 2-fluoride to calculate the grams of tin 2-fluoride. All right, let's plug in those molar masses and the mole ratios. Again, we have 117.5 grams of tin 2-fluoride. Oh, I did see a typo here. Over here, should have typed in the 30.00 grams of hydrogen fluoride. That'll make those calculations go a little bit better there. All right, so again, here's another flow chart. Again, here we're actually going to start with volume. We can start with volume. And if we just multiply the volume of the substance, as long as it's in milliliters, if we multiply the volume of a substance by its density, that'll actually give us a mass, because the volume portion of density will cause that unit of volume to cancel out. We'll be left in mass. You can do something very similar if we're given the amount of the substance in formula units or in molecules or particles. We can use Avogadro's number as a conversion factor, and we can go directly into moles of the substance. Then from either of these spots, we can continue with any of these stoichiometric calculations that we want. All right. These are flowcharts that are very good for your problem solving help. So as you go through your homework sets, you're definitely going to have access to these flowcharts here. Keep them open, use them. Don't try to do the first few of these problems off the top of your head. You definitely want to get some help through your first few times through. Alright, that's the end of the video lecture for this section. If you have any questions, be sure to ask them, and I will see you next period.